Hello, welcome to my explanation of my three-dimensional visualization of the zebrafish olfactory sensory neuron motion analysis. So this is the outcome of my final algorithm that produced the 3D model, and as you can see here, this is all of the TIFF images stacked up on top of each other. And as you can see here, this indicates the frame number. So all of these are stacked up on top of each other to form a 3D model that shows the nerve motion, the neuron motion, as time progresses. Of course, it's very hard to see how the neurons move, so that is why I also implemented a tracking method where it tracks single neurons individually, one at a time. And also at the bottom here shows the 2D version of the zebrafish neurons and all the points that it tracks. And currently t equals 1, or the frame number 1, I am tracking the first point, and that is indicated by this yellow dot. And also it's difficult to see here, but if I make the model more opaque, give it some time, then you can also see the number of points. You can also see the neurons, but it's still kind of blurry. So I'm just going to go ahead and remove the 3D image. Now, as you can see here, these are all the points, all the neurons this is one single neuron and is detecting its motion throughout the frames. So as you can see here, this is the 2D projection of it, and this yellow dot is the same as this yellow dot, so it is basically it is tracking this neuron. So as I increase the frame number, so if I go from frame 1 to 2, it will keep going. As you can see here, it's showing each frame at a time, and it's also tracking the same point as it goes. And you can see as it progresses, the same here as well as here, it moves and tracks the neuron as time progresses. I'm currently flipping this because this is actually the more accurate view. But basically, the blue lines are the interpolation lines. So interpolation is basically a method where, well, in this case, Mathematica is predicting the path at which the neuron was taking. And of course, some of them are very drastic because they do go all the way down in some points. So you can see here, if I go back a little bit, you can see it did dip down right there, and it looks like the interpolation did estimate that it was going down too much, but interpolation is it is close, but it's not perfect. But it still tracks pretty well, and you can see the movement of that one neuron. So one thing, if you read my report, that I did differently was I used an image, in this example, image 1, and I used that to compare it with all of the other images to track the points. And that is because image feature track, which is the command that I'm using to track all these neurons, the number of points that it actually finds depends on the first image you put in, or one puts into image feature track. So basically what this does, it puts image 1 first inside image feature track and then the rest, so that the number of points is determined basically by this image. So if I use image 2, for example, again, a whole different set of neurons are detected throughout each frame. And this is really great because I was able to detect much more neurons, many more points, because I was able to use different images and find more different points. Basically, so you can just see here the difference. So if I say, if I use image 1, I only find 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 points. But if I use image 2, it's much more, many more points. And you can see the yellow dot here again. It's the same thing. So it will track all the way. And also, if you don't want the red dots in your way, you can also. And sometimes the interpolation does stop in the middle because the data does get too chaotic. But one other benefit about this method is it actually a majority of the points that it found actually tracked it all the way to the last frame. So that's really great, because I remember having a lot of problems with not finding any points or having the interpolation stop only a quarter of the way, but majority of these did actually go all the way. And also, and using this image, I found a lot more points, and I can switch from each point. So this is point 1, so this is point 2, point 3. In this case, this represents a different neuron. So this is neuron number 3, for example. And you can see its movement. This is it's a much smaller movement. If I get the points back, yes, you can see how it moves, and it's very interesting as well. As you increase the frame, that top one doesn't move that much. However, it does very slightly. And if you keep switching from point to point, you can see all these different types of movements, especially this one right here, the one at the tip right here. It looks like it doesn't move that much, which seems to be true. And the last thing I did was also show Fourier graphs. This is using fast Fourier transform to actually, yes, it's using the Fourier command in Mathematica, and I put it there because there might be some application for it, but at the moment right now there isn't.